The broadcast is now starting. All attendees are in listen-only mode.
Hello there and welcome from Ventura, California to today's webinar, Space Weather and GNSS Sources, Characteristics, and Mitigation of Effects, sponsored by Novatel and inside GNSS and hosted by WebAttract, your end-to-end solution provider for informational webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they discuss space weather effects on GNSS systems and what you can do about them. We've invited you along with over 450 professionals from 49 countries and 30 states and provinces representing a variety of industries. Over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Before we get started, Glenn Gibbons, editor and publisher with Inside GNSS, would like to take a moment to welcome you and introduce Jason Hamilton of Novatel and Demos Gebra-Egzabher, who'll be moderating the main portion of today's webinar. Glenn?
Thank you, Lori. And indeed, welcome to all of you to the latest installment in the Inside GNSS web seminar series. Today's presentation is sponsored by Novatel, and it addresses a subject facing the GNSS community in the very near future. That is, the current solar cycle and the prospect of increasing atmospheric effects on GNSS receivers during that cycle. Inside GNSS reaches more than 35,000 readers around the world with its print edition and thousands more with our digital magazine and newsletters. And based on the number of registrations for today's webinar, it's clear that space weather is a matter of considerable concern to many of you. I encourage those of you viewing our presentation today to contribute to the webinar yourselves by responding to the questions in our online webinar polls and sending in your questions for the live question and answer periods during the event. And now I would like to invite Jason Hamilton, Director of Marketing at Novatel, to say a few words about today's event.
Thanks, Glenn. On behalf of Novatel, it's my pleasure to welcome everybody to today's webinar on the impact of space weather on satellite-based navigation. Thanks, everybody, for joining us today. With the upcoming Solar Max, this is a topic of great interest to our customers in a range of different applications, from precision survey to precision agriculture and military guidance and control. We're excited to hear what these leaders in space weather research have to tell us about their research in this area, and also to hear what the webinar attendees themselves are experiencing in the field as we start to see more atmospheric interference on GNSS as we come up to Solar Max. Back to you, Glenn.
Thank you, Jason. Now I'd like to introduce our moderator for today's web seminar. Demos Gebra-Egzabher is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities campus. His research area is in navigation, guidance, and control of aerospace vehicles. Demos, it's great to have you with us here today. Welcome.
Thank you, Glenn. Greetings, everyone. And on behalf of Inside GNSS and our sponsor, Novatel, I'd like to welcome you to today's webinar. We have two leading experts in space weather and GNSS and its effects on GNSS today lined up, and I'm pretty sure everyone, from the new users of GNSS to those who are seasoned in the field, will get something useful out of this webinar. So just to get a pulse on our audience, we would like to take a quick poll at the beginning. Lori, if you could get the first poll.
Sure thing. Coming up on your screen, folks, you will see that first poll. We'd like to hear from you with respect to space weather. I have a very good understanding of, and please select one of the choices. Its impact on GNSS, but not the physics behind it. The physics behind it, but not its impact on GNSS. Neither its impact on GNSS nor the physics behind it. Or perhaps I don't fit into any of the above categories. All right, let's go ahead and have a look at those results. And looks like a nice spread. Any thoughts on those, Demos?
All right, so yes, looks like we've got folks from all the different spectrums of I guess experience and knowledge of space weather and GNSS. So as we said, I think today's webinar will have something for everyone on space weather. So with that, let me go ahead and introduce our panelists today that are going to be presenting the webinar. Our first panelist is Anthea Koster, who is a research scientist in the Atmospheric Science Group at MIT's Haystack Observatory. She received her PhD in space physics and astronomy from Rice University in 1983 under the guidance of William E. Gordon, the founder of the Arecibo Observatory. She has been involved with GPS since 1985. Her professional interests include physics of the ionosphere, magnetosphere, and thermosphere, GPS positioning and measurement accuracy, and space weather and storm time effects. And our second panelist is Joe Conchis, who is a space scientist at the NOAA's National Weather Service Space Weather Prediction Center in Boulder, Colorado, National and International Center for Space Weather Services. His primary responsibility there involves working with customers to understand their needs and define the appropriate space weather products and services for them. He is a past secretary of the International Space Environment Service, ISES, and a member of the editorial advisory board of the quarterly journal GPS Solution. Mr. Conchis holds a BS in Aerospace Engineering and a Master's, the Bachelor's of Science from the University of Notre Dame and a Master's from the University of Colorado. All right, so with that, let's go to the first part of our webinar, and the presenter for this part of it will be Joe. Joe?
Thank you, Demos, and hello, everyone. Thank you for being here today. And the topic is space weather and the effect on GNSS. And what I'm going to do to start is to give you a description of what space weather is. You've heard about the solar activity cycle. You may have seen some of this in the media in the last couple of years. So I want to give you a sense of what we do here in Boulder as we go about our predictions day in and day out to try to give people what they want. Now, on this page, on this first slide, on the left-hand part of it, you can see a graph of the current solar cycle. We're in solar cycle 24, and as you can tell from sort of the ratty month-to-month data that show up here, it kind of varies quite a lot. We're still in the ascendancy of solar cycle 24. What this really means is that we're counting sunspots here, and sunspots are important as proxies for space weather activity because they show the strong magnetic fields that the sun creates over a period of about 11 years. And the sun does this slow dance as it generates magnetic fields. The magnetic fields percolate up to the surface, they intensify, they get twisted, and they erupt, and that's what gives us the space weather that we commonly refer to. Now, every now and then, the dance does a pirouette, and we actually get an episode, maybe a week, maybe 2 weeks long, of enhanced space weather for a period of time. So I want you just to think of this more as a season rather than a month of strong space weather, because it really is probably for the next few years that we're going to see elevated conditions that would affect GNSS. On the upper right-hand side of the page, I'm showing you about 150 years worth of data. And just focus, I guess, on the point that, again, you see this roughly 11-year periodicity. You see the most recent cycles being somewhat stronger than the past cycles. So we're in the midst of it right now. Now, you may have heard that this current solar cycle isn't as strong as some had predicted, and maybe even not even average. The red line on here shows the average solar cycle behavior over the past, again, a couple hundred years. And we probably are going to come in at average or below average, but I don't want you to get misled by that. Because we know back in 1859 and also in 1921, there were very strong geomagnetic storms that occurred. So you can have pulses, even in small cycles, relatively small cycles, where the Earth's magnetic field becomes very disturbed, and hence the Earth's ionosphere becomes very disturbed. At NOAA, we've created a space weather scale similar to the hurricane scale and the tornado scale that you're familiar with, perhaps. And then we've ranked them sort of from top to bottom. If you had a race from things coming from the sun, the winner would be the electromagnetic emission, the solar photons, and the radio emission that comes with the solar flare, and that takes only 8 minutes to get here. The next thing would be the charged particles, the electrons and the protons that are accelerated at times, and those might take some minutes to an hour, maybe even a little more than that at times to arrive. The main focus of this time today, though, is the magnetized plasma, the geomagnetic storms that are the slowest to arrive, fortunately. So if you're a forecaster, you have the best shot at predicting these, and these are the things that really affect GNSS. So taken one by one, the solar flares start, all of this of course starts with the strong magnetic fields at the sun, and on the left-hand panel you can see sunspots which denote the strong fields. Moving to the right, you can see the flash phase of the flare, a very violent sudden release of energy. It takes again about 8 minutes for that energy to reach the Earth. And the kinds of things that are typically impacted are dayside stuff, radars working on the day side of the Earth, HF communications on the day side, and even in some cases GPS can be affected for a short period of time. The next type of space weather, the solar radiation storm, also begins with an eruption at the sun. In the middle panel I show satellite measurements from the GOES satellite with 3 energy bands that quickly you can see go up almost in concert as the event progresses. And one of the typical effects of a solar radiation storm, given the way the Earth's magnetic field sets up, is actually that radiation environment at high latitudes can be affected, and things, well, we'll get to the impacts here in a minute, but things like HF radio at high latitudes, satellite operations, even manned spaceflight issues come up with solar radiation storms. Now the last of the 3 is the geomagnetic storm. If you occult the solar disk, you can watch the electrons as they scatter light from the sun, and in these two pictures, you see a coronal mass ejection leaving the sun. Now these are large. They're on the order of 10 to the 16th grams, which don't do the back of the envelope too fast. It's about 10 trillion tons of material. They lumber along at about 1 million to 2 million miles an hour. And these are the things that when they go by the Earth, they create the strongest magnetic storms. They have some ill effects on satellites, on aircraft operations, on even electric power grids. Even pipelines are affected during geomagnetic storms. Now, if I can make you into a space weather forecaster for a minute, this is how we go about our business here to predict these things. The 2 pinwheels on the left-hand side show solar wind with the sun being in the middle and the Earth being out here at 3 o'clock roughly. There are 2 satellites, the stereo satellites, which we'll talk more about later, in this diagram are at the top and at the bottom. You're seeing density at the top, you're seeing speed at the bottom, and you're seeing a meridional cut over here. Well, when a coronal mass ejection occurs, forecasters measure, they detect it with the satellite instruments, they measure its properties, its speed and its width, and they put it into this model, a propagation model, to see A, if it's going by the Earth, and B, if it is, when that's going to happen. About 1 million miles upstream between the Earth and the Sun is the ACE satellite, which has plasma instruments on board to watch the solar wind as it goes by. So that gives us about an hour, maybe a half an hour for the fastest ones of warning that a geomagnetic disturbance is about to occur. Now the ground truth of this is a ground-based magnetometer, one of which we have here at Boulder. Now this year there have been a number of episodes of enhanced space weather, and back in March was probably the first big one. There was actually last fall a couple of episodes where the WAAS was affected in September and October, but all things considered, they weren't as dramatic as the one in March. In March, we had the trifecta. We had a Category 3 solar radiation storm, radio blackout, and geomagnetic storm. The solar, so taking, I guess, in reverse order, the radio blackout is shown here with the solar X-ray measurements from the GOES satellite. The solar radiation storm quickly occurred, started very fast after the eruption at the sun, and that also is shown here in the GOES data. And then the geomagnetic storm, the one that had the most effect on GPS and GNSS operations, actually, as we would expect, was slower to arrive, but the prediction was pretty good. We got it within an hour or two of when, with a few days lead time. Again, this is the model that we use, and here you can actually see the disturbance in the model. And down here in the lower right-hand corner is the index KP, which we'll talk about more later. but actually showed the evolution of the geomagnetic storm, which reached Category 3 level. Now you might wonder, how do we before we go to this, here's some other impacts that occurred during that episode in March. Aviation had some polar flights were rerouted due to communication issues. I'm not going to read all of this, but there's some communication issues, and the FAA-WAAS had some issues as well. Power industry saw low-level induced currents. Satellite industry had some effects based on this activity then too. The way that we sense and measure and monitor space weather actually is with a fleet of satellites, some of which are owned by NOAA, some by NASA, some by the European Space Agency. And I guess the primary ones I'd like to highlight for you now is the stereo satellites. One going from the lower left-hand corner is moving away from the Earth. Stereo ahead is running ahead of the Earth, and they afford us a perspective from the sides, and we can watch coronal mass ejections come off the sun. And with the benefit of satellites right on the Sun-Earth line, the SOHO satellite, the ACE satellite, which we've already talked about, we can actually see these projectiles as they're launched from the sun. We have a good sense of their direction. We have a good sense of their speed. And with these other satellite assets, I'm not going to describe all of them to you now, we have a better ability than ever to detect space weather as it occurs at the sun and get the warning out to affected parties, in this case the GNSS community, of the potential of a geomagnetic storm that may have a detrimental effect on their operations. So just in summary, we are in the season for enhanced space weather. We're in the ascending phase, near the maximum of solar cycle 24, and we expect to see more eruptive activity over the next few years. So I'm going to stop there, and I'll turn it back to Demos.
Thank you, Joe. And now that we've just talked about the basic physics of space weather, Anthea will talk about the direct impacts it has on GNSS. Anthea?
Thank you, Demos. To begin with, I want to just review the three basic parts of the GPS satellite signal structure. And the first, and this is actually the carrier phase, and this is where you get the high accuracy that we all want. It comes from the carrier phase. And we use this to measure Doppler and range. The next is the code modulation that we impose on top of the carrier phase. And that basically is used to identify the satellite, and it can also be used to measure the range. And finally, on top of all of this is the navigation data. That gives you information about the satellite orbit, it gives you error correction, and it tells you something about the satellite's health. All three of these are combined together to make the GPS signal. Now, to make range, which is probably one of the most basic things that is affected by space weather, you start with your code, which is transmitted at the satellite, and basically it's transmitted at time TS, and then it is received at the receiver at the time TR. And if you look at the difference between these two times, you have the delta T, the time that it took for the signal to leave the satellite and to reach the receiver. And if you assume that this information is traveled at the speed of light, you have your first pseudo-range measurement. Now you can also do something like this with the phase. The only problem is that you don't have the exact information about which phase front you're actually receiving at the receiver. What you can do is count the number of phase fronts that are crossing the receiver. So there's this M-pi ambiguity, and that's a very important thing to remember. So although the phase is giving you the most accurate measurement, you still have an ambiguity built into it. Now, to do your positioning, you have a receiver on the ground, and you are tracking 4 satellites. Each one of these satellites is sending you information about its position, so its location, and again, from that you get the time that it took to actually travel from the satellite and be received by your receiver. So if you have those for actually 4 of them, you can solve for your position in 3 coordinates, x, y, and z, but you also solve for a bias of the clock that your receiver is using. And that's because although the satellites all have atomic clocks, your receiver probably doesn't. So you really want to solve for the most accurate time you can with your receiver. Now, in the perfect world, you would have a perfect result, but we don't have a perfect world. There's error sources in everything. The first thing is that the satellites aren't really exactly telling you where they are. There's built-in errors in this ephemeris. The GPS clocks, even though they're typically, it's a combination of 3 or 4 different atomic clocks, there's still errors embedded in them, and they try to account for it, but there are some errors. Your receiver has some noise. Your multipath environment is important, and it does depend on where you put your antenna and how much scattering there are from other structures. But the most important is the additional delays that you're going to have from both the troposphere, which is the lower part of the atmosphere, and the ionosphere. Now, just to give you a sense of where those regions are, the ionosphere is typically defined from about 100 kilometers to about 1,000 kilometers, and it's the region of free electrons that are in the atmosphere, and they affect the electromagnetic radiation that is propagating through. You also have the troposphere, which is defined typically from about 0 to 10 to 15 kilometers above the Earth. And that affects your electromagnetic radiation, both due to the water molecules, so you can think they have a dipole moment, and just the background pressure and temperature. But in this talk, we're really focusing on the ionospheric part. Now, what does the atmosphere do to your radar radio waves? It bends, so it has an elevation refraction term. If you're actually tracking a GPS satellite in the tropics at low elevation, you can sometimes actually see the satellite when it's below the horizon, meaning what you observe is actually higher than what the true bearing is for the satellite. And that's because the wave is bent as it's propagating through these regions where the index of refraction is changing. The other thing you have is a range delay. You're assuming that the wave has traveled at the speed of light, but it hasn't. It's traveled slightly slower. And so the true range to the satellite is, the true range to the satellite is actually less than the observed range. And what we have to account for is how much delay has the ionosphere added to your solution. So the index of refraction, which is probably the most important term that you need, in the ionosphere it looks like this. And this is a pretty large plasma physics equation. But for GPS frequencies, which are fairly high, we can actually remove everything here and everything here. So all of these terms cancel out, and we're left with 1 minus x. And x is the ratio between the plasma frequency and the frequency of the wave you're propagating at. So you have plasma frequency, which is dependent on the electron density and a bunch of constants. All right? So if we actually now look at how we can get rid of all of those other terms, we're left with the index of refraction being approximately equal to 1 minus a, where a is a constant, times the electron density divided by the frequency squared. And this translates to a delay in your range due to the group velocity of 40.3 divided by f squared times the integral of the electron content along the line from your receiver to the satellite. So this value here is what we call TEC. Now, what I've shown you here is what you would expect for the velocity, the group velocity. But if we were actually talking about the phase velocity, this term right here would be a plus. And you can actually, in the ionosphere, it appears as if the phase velocity is faster than the speed of light. It's not, and that's because there's no information transferred via the phase. It's just apparent velocity, so that the apparent velocity is exactly equal or just has a different sign from the group velocity. This minus becomes a plus. So I want you to remember that. So to give you another sense of how the ionospheric range delay actually changes as a function of frequency, remember we're talking about the true range and this observed range, which this little delta extra range, which is equal to 40.3 divided by f squared times the TEC. And for different frequencies, for S band, which is higher than L band, we can, for a value of about 50 TEC units, which is what we might see now in the equatorial region, you would have a delay of about 2.4 meters. But for L band, you would have 12 meters. For UHF, 100 meters, and for VHF, almost a kilometer. Now, if you're looking at low elevations, this value would go up by a factor of about 2. So again, our 12-meter correction at L band for low elevations will be about 26 meters. Now, I want to show you this to show you the difference between the pseudo-range data, which is shown up here, and this is the carrier phase data, or the carrier phase solution for the ionospheric delay term. Immediately what you can see is that the noise on the code data is a lot larger than it is on the carrier phase. It's about 2 orders of magnitude larger. You can also see that we've set the carrier phase here at 0. The data, we don't really know. There's that m-pi ambiguity. But we'd like to use this to smooth our code data. And that's typically what's done in the ionospheric community. We get the wonderful shape, the noise, the less noise from the code's carrier data, from the code data, and we use it to smooth the code data. So that's called carrier phase smoothing. Now, another problem for most GPS users is scintillation, or for some GPS users. And that's where, when we have in the ionospheres, we have irregularities forming. Remember, we have a plasma with free electrons and ions and a magnetic field. And if you get any disturbance in that region, these electrons can line up along the magnetic field lines. And so what happens is you have an incident wave coming from the GPS satellite, which enters this region with uniform phase and uniform amplitude. But as it propagates through this region of the irregularities, and you can think of them as being like little dipoles scattering everything, what comes out is a wave emerging that has non-uniform phase and quasi-uniform or non-uniform amplitude. And your receiver on the ground sees basically a diffraction interference pattern. And in addition, to complicate this whole picture, the irregularities themselves are moving with the plasma drift velocity, and your satellite is moving at a satellite velocity. So this is not a simple situation. Now, there's 2 primary regions where you can see scintillation, and that's one in the polar regions, as you can see here, and that happens all the time. It doesn't really matter. It's not a day-night thing. You can also see them in the equatorial region, and there it typically is sunset to dawn. These irregularities start right at sunset, and then they can last all the way till the morning. What you see here, this is 3 different GPS satellites being tracked, and this is the amplitude scintillation. And you can see that where we had before it got into the region where the bubbles were, we basically had a very smooth signal. Then all of a sudden the amplitude is going up and down quite a lot. For GPS users, the primary issue here is loss of lock. For other people, for example, for radars, the primary issue is degradation of coherent integration capabilities. And then there are further other people who are interested in communication channels, and they get closed when you have regions of scintillation. So it's not just an issue for GPS users. So to conclude this section, I just want to say the ionospheric parameters that GPS can use to measure are: ground-based receivers can measure total electron content, and the scintillation parameters, which give you some information, S4, it's defined here, gives you some statistical information about the amplitude variation in the signal, and sigma phi, which gives you again some kind of statistical information about the phase fluctuations in the medium. From space-based receivers, you can measure electron density profiles and scintillation parameters, S4 and sigma phi. So now I'm turning it back over to Demos.
Thank you, Anthea. So we're going to take a pause in the presentation here and open the floor to questions for our experts. And so the first question, and I guess I'll pose this one to Joe, and it's from Robert. And the question is, there have been predictions that cycle 24 could be the last major cycle for the several 11 cycle year periods. Do you have any information on this?
Yeah, that's a very good question, because there has been an ongoing study, and there's a group at Kitt Peak National Observatory in Arizona that has, for about the last 15 years, measured the field strength, the intensity of sunspots. And they claim that over the time of their record, the actual magnetic field strength in a typical sunspot has declined. And if it continues to do so, the supposition is that the field would not be strong enough to create sunspots, and we could be entering into another extended minimum. Nobody's old enough to remember this, but there was a 70-year minimum from 1645 to 1715, coincident with the Little Ice Age of Europe, the so-called Maunder minimum. So we know the sun can do this, and there have been lesser prolonged solar minimum periods even since. I'd have to say that the jury is out on that one right now. The data record isn't very long. There's some noise issues, I think, that some people bring up. So we're as interested as anyone in watching how that's going to play out.
Well, thank you, Joe. Let's see. So here's another second question, and this one I think I'll let Anthea answer it, and it's from Andrew, and it's about GNSS vulnerability in general. Is there a paper or any resource that shows a list of solar events that have affected GNSS, possibly ranked for severity with the symptoms of those events?
A single paper, there's numerous papers, but I can't think of one. There is one by Dougherty et al., which describes some of the initial effects on the WAAS system during the October and November storms of 2003. So I would recommend that, and I think that was published in GPS Solutions. But the other thing I would do is just tend to scan through the ION journals, or not journals, but the proceedings, and see which ones there are. But having one general paper, I'm not really sure of exactly.
Joe, would you know of any resource that may?
Yeah, I'm trying to think of that too, Demos, and I would agree with what Anthea said. I mean, there are a number of them out there. Maybe if we could, table this question and maybe put our heads together when it's all done, we can come up with a better answer. But certainly you can find information, there's no doubt. It's just trying to point you in the right direction.
Okay. Right, so here's another question. This one is also from Andrew, and I guess I'll point it to you, Joe. And the question is there a place, a web page, that I can see the current up-to-date version of the sunspot activity diagram that shows solar cycle?
Yes, there is. You can go to the Space Weather Prediction Center website, and then under, you have to dig a little bit, but under the Data and Products section, which is on the left-hand sidebar, you can click on that, and you can get the monthly solar cycle progression charts, both for sunspots and F10.7, as one place where you can get the most recent stuff. I think you can also get it from Brussels, from the Sunspot Center there. But if you want to send me an email, I can give you some links rather than have you hunt around too much.
All right, let's see now. Let's go to another question here, and I guess I'll assign this one to Anthea. And the question is it possible to predict equatorial scintillation, and is there any group doing that?
Is it possible to predict equatorial scintillation? The answer is there are groups that are trying to do it. I would talk to the people at Air Force, the U.S. Air Force Geophysics Laboratory. They have a program called CINDA, and CINDA basically has a network of receivers and other instruments around the equator, and they're trying to actually capture the development of scintillation as a function of time. They also incorporate satellite observations. Now, what they're doing is trying to really nowcast and predict a little bit ahead. I don't know if there's something that could predict several days ahead. As I said, in the equator, scintillation typically occurs at sunset and lasts through the night. So if you can see where one of these bubbles actually occurs and then track it moving, you have some sense of which region of the sky is causing the scintillation.
Joe, there's a similar question along those lines. Is there something that you would want to add to that? It's
well, I'm sorry, go ahead, Demos.
Effectively, it's the same, more or less similar question as from Rajesh. Is there any way to predict scintillation for a particular region in the world?
Yeah, that's a really good question. And just to add to what Anthea said, there's also work going on here at our laboratory here in Boulder to try to predict equatorial scintillation. Dave Anderson and his colleagues are looking at something called the pre-reversal enhancement, and if the person who submitted the question can send me an email, I can put you in touch with him as well. As far as scintillation for any particular region of the world, we've been told by customers that this would be a great step forward if we could come up with the ability to predict this. And I have to say that it's been pretty elusive as a target, because it's just very, very difficult to do. Anthea mentioned that for the equatorial region, the post-sunset time, typically speaking, is when it happens. But it'd be nice to be able to say, thinking back to the last solar maximum, perhaps, that for one of these episodes of enhanced space weather, where we could say that the scintillation conditions are going to be the most acute over the eastern seaboard or the west coast, over Europe or Africa for that matter. And I have to tell you that I'm not aware of anyone or any group that's able to do that to the degree that it could be useful to a customer.
Okay, thank you, Joe. Here's another question, and I guess it's from Luis, and I'll ask Anthea this question. Could you please characterize the difference between polar and equatorial region behavior in terms of phase scintillation and intensity of scintillation?
Well, that's actually kind of a trick question. Basically, right now, most receivers see primarily phase scintillation in the polar region, but that may be because of the way that the receivers are handling some of the inside software, and that if we use wavelets instead of Butterworth filters to actually detrend the data, we may actually see both the amplitude scintillation and the phase scintillation. So right now, if you were to ask me, I would say in the polar region, what you see is phase scintillation, and in the equatorial region, you see both amplitude and phase scintillation. But our receivers may be deceiving us just because of the way we're handling the detrending part before the signal actually goes into the phase lock loop.
All right, thank you, Anthea. Let's go ahead and I guess move on to the second part of our webinar. But before we do that, let's do a quick poll. And Lori?
Absolutely, and folks would like to hear from you. With GPS modernization and the advent of other GNSSs, the ionosphere errors and effects will, in your opinion, be completely eliminated, cease to be the dominant error source, remain the dominant error source, or I'm not sure how GPS modernization will affect the iono errors. Demos?
All right, so looking at it, looks like most of our audience believes that will remain the major error source, and but definitely things are going to change with the newer GNSS, the newer signals coming in. So in the second half of this webinar, we'll talk a little bit about those. And so let's go to the next part of our webinar, and Thea will talk about the impact of space weather on the GNSS PVT solution, and that will answer some of the questions that we brought up on that poll. Anthea?
Thank you, Demos. So the first thing that I want to say, when we have one of these large geomagnetic storms, we will see something known as storm enhanced density. And what you see here, this large red, where you see the red is where you see very, very high TEC values. And I should specify, someone pointed this out, when I say TEC here, I mean TEC units. And that means it's number of electrons times 10 to the 16th divided by meter square. It's a standard set of units for ionospheric science. So basically you can see that we have this very, very constrained region or plume of ionization that's being generated during the storm. And what are the impacts on GNSS? Well, the plume extends 1,000 kilometers east-west. We have gradients of 30 to 50 parts per million near the edges of the plume and at the base of the plume. And we see this plume not just over the U.S., but we also see it conjugate in the southern hemisphere. At this time, it would be over South America. And you'll see in the next movie that I have to show you, it actually rotates. As the Earth turns, you're going to see that this plume is actually moving, sweeping across the U.S. So this actually causes a lot of problems. These large gradients, I mean, if you were a receiver on the edge of a gradient and you're actually tracking different GPS satellites, your own position is going to be affected by these different, different positions that you'll be calculating. Now, it doesn't just affect the mid-latitudes and the polar regions. We also have geomagnetic storm effects that occur in the equatorial region and also over Florida. This is from a 2000 storm, one of the big ones. And this black shows us a site in Guyana, which is in the equatorial region. And basically you can see that right at about 2100, the TEC, which was measuring about 100 units, drops down to almost zero within an hour, couple of hours. And the TEC at Key West, which was measuring a little bit below 100 units, goes up to well over 200 TEC units. So we have this very rapid changing in the distribution of TEC around the globe. The storm impacts for the FAA, the Wide Area Augmentation System, it was seriously impacted during the Halloween storms of 2003. For 15 hours on October 29th and 11 hours on October 30th, the ionosphere was so disturbed that the vertical error limit exceeded 50 meters. So basically that translates into commercial aircraft being unable to use the WAAS system during that time period for precision approaches. And also, just to show you how fast that can change if you were trying to land a plane in either Pittsburgh or Washington, basically this is in minutes at the bottom, local time, and basically the range error went from 32 meters to about 5 meters in less than 10 minutes over Pittsburgh. And in Washington, D.C., we had more of a roller coaster type effect, where at about 8:50 it was 25 meters, it drops down to about 7 meters, it goes up again to 15 meters, and it goes back down to 5 meters. So you can see in this kind of environment, it's really hard to get an extremely accurate position. Now, another thing that is worth considering is what kind of user are you? Are you a differential user? Do you want very, very precise differential? Are you interested in solving for the phase ambiguities, or do you just want the best kind of values you can get over 100-kilometer baselines? Typically, in differential GPS, you not only are getting solutions from all of your GPS satellites, but you have a known, very highly not a receiver, but a receiver with a radio link that really knows exactly where it is. So it's been surveyed, has a very high knowledge of where its position is, and it's sending that information to a user. And spatially correlated errors are reduced because of this technique. So typically, For 100 kilometers, you can get 1 to 3 meters. And people who use this are the United States Coast Guard, the Canadian Coast Guard, and also the Department of Transportation. I think this is called Nationwide Differential GPS Service. So a lot of people are using this kind of technique to get the accuracies they want. Now for marine horizontal positioning, and I would say think of a barge in a foggy situation, they want to know where their horizontal position is to within 10 meters. So what would happen if, this is actually an example of if you were trying to do differential positioning where you were solving for the phase ambiguities. And to do that, you really have to knock out the ionospheric errors. So we had a receiver here at Lincoln Laboratory, another one at Millstone Hill. They're separated by 25 kilometers, so not very far. During a large geomagnetic storm, and again, this is a KP=9 event, if you actually looked at the first difference of the ionospheric delay between two receivers spaced only 25 kilometers apart, you can see that in many cases they're over 0.2, right? And 0.2 stands for 20 centimeters. That's the full wavelength of your GPS signal. So in that time, you really need fractions of a wavelength to actually go back and try and solve for your n lambda ambiguity. So basically, during this time period, you could not really do very, very precise positioning. Now for your the larger baselines, 100-kilometer type baselines, just to give you a sense of how large these horizontal position errors can be during the storm enhanced density effects. We have a receiver here, and we're looking at 4 or 5 different receivers around it that are about 100 kilometers apart. And you'll see as we move through this structure, we can have errors. On one day, we had horizontal positioning errors that went up to 20 meters. And on the second storm day, we had horizontal position errors that went up to 25 meters. So yes, we can have a big problem for differential users due to space weather events. Now, equatorial scintillation, and I said typically this happens at night where we have these bubbles rising up. We have the sunset, and then we have bubbles rising up in the plasma. Inside this plasma, that's where we get irregularities forming, and these irregularities are doing the scattering. And what happens is you get this very large amplitude scintillation. This is the L1 signal intensity, and you can see there for about 20 minutes, it's just for this one particular satellite, we're going all over the place. Now, just again to give you an example, this is from Ascension Island, which is right here, right near the equator. There was a time period where almost all 7 of the satellites, I think it was tracking 8 satellites, and everywhere where it's red, it was observing, the receiver was observing pretty serious scintillation. And you can see on this day there was only 1 satellite pass that was basically not suffering from scintillation effects, which would be a problem. Now, in the polar region, and remember, as I said, this may be an artifact of the way detrending is happening, but we typically look at sigma phi, so the phase fluctuation. And anytime we have a sigma phi of greater than 0.6, 0.65, that's when the receivers have trouble. And so we were using specially designed receivers here. One was at McMurdo and one was at the South Pole. And you can see that there's like a 2-hour period, and this was actually associated with a storm enhanced density effect, where we definitely exceeded this 0.6 number in sigma phi. Now, one last thing to be aware of, which is a space weather effect, is the solar radio burst. And basically what happens here is that we're not really looking at effects on the GPS signal itself per se. We're looking at the noise floor in the L-band region going up. And that's because you have this burst of energy from the sun, and some of it is in the L-band frequency range, and so your noise floor jumps up. And this was predicted actually early on, but it was seen again in 2005 by a Cornell graduate student who was actually had designed his own receiver, and he was measuring the signal attenuation. And what you can see, this is the same satellite, PRN-25, on 2 different days, September 6th and September 7th. And you can see he noticed that the signal-to-noise ratio dropped for 2 different time periods. And when he went back, the places where it dropped were correlated with the solar radio burst. So they then predicted or said, we think that this could be a problem. And as I said, other people had mentioned it before, but the prediction came truer earlier than anyone expected, because we were in 2006, we were in the middle of solar minimum. So nobody really thought this might happen, but we had a very, very large event which disrupted basically a lot of things all at once. And it actually, we made the news for this observing the solar radio burst. It was published in the New York Times and also the Washington Post. And just to show you what happened, what we have here, this actually came from JPL. They operate the IGS network, and basically this network is designed with providing very, very high precision data. And so I want to show you this line here. This shows you the sunlit part of the Earth, and what you're looking for is where this little green, these are all different IGS receivers. When they turn red, they were not able to track, and they are doing high precision tracking. And this at the bottom is showing you where the solar radio burst. This full time period is only about 10 seconds, but I want you to watch it. Okay? Now the bubble is showing you what's happening, and it's about to go into the solar radio burst, and notice how many of these receivers went red. So this is a problem that we need to be aware of as we go through thinking about solar radiation. So with that, I turn it back over to Demas.
Thank you, Anthea. Now the next phase we're going to talk about is the impacts on GNSS, is to look at the way of mitigating these impacts. So I'll let Anthea take over again and tell us a little bit more about mitigating techniques. Anthea?
So just I want people to think about how a receiver actually works, and we're going to go from right to left. You begin here. The first thing the receiver does is try and decide whether a signal is present. And once it acquires a signal, then it goes into a frequency lock loop. And from that, it gets an estimate of the velocity. It uses that velocity to detrend the data. It goes into code lock. And then you go into the phase lock loop. And this is the most sensitive part of the receiver, and where you can lose lock fairly easy. So as long as everything is okay, we're tracking fine. But once you lose lock of phase, you go back, then it goes back to the frequency lock loop. If the amplitude measurements are not good, it goes back to reacquiring the signal. So to begin, the general GPS receiver limitations in a scintillation environment. 1, with phase scintillation, it's generally not a problem at L1, but it is a severe problem for semi-codeless L2. And that's because the very narrow bandwidth they're using in the phase lock loop, coupled with the erroneous aiding with the L1 phase, it's a real problem. Now, amplitude scintillation is a primary culprit for loss of lock at L1. And that's because deep, long fades that you get from the amplitude scintillation steal the signal from the phase lock loop. A narrower bandwidth is better, but 1, it could require a better oscillator, and 2, you can get false alarms from lock detectors during fades, apparent loss of lock. So this is a problem. You can also lose data symbols from the S-bass signals during amplitude scintillation. Now, there are certain receivers that are out there that are specially designed to actually measure both amplitude and phase scintillation, and I'm going to kind of review how that's done here. But just keep in mind that there are specifically designed receivers to do ionospheric measurements, both S4, sigma phi, and TEC. So to measure amplitude scintillation, this is fairly straightforward. You measure the GPS signal plus noise, and you remove the noise power to the extent possible, so you're left just with the signal power. And then you do some detrending. You're actually able to look, depending on how you detrend the data, you can basically take the multipath fading out and separate the scintillation from the multipath fading. And averaging proves to be more stable than filtering, but it results in a higher S4 due to multipath fading. Phase scintillation effects. The GPS must track the signal phase using a phase lock loop, and that's the weakest link in a GPS receiver. Now, you can think about it. The measurements actually include perturbations of the receiver and satellite oscillators, and these perturbations cannot be removed with detrending. They also include signal Doppler, multipath, ionospheric TEC, and oscillator frequency offset. All of these can be removed with detrending, and one of the things that newer design things are looking at are the ways we detrend the data now. Typically, the measurement bandwidth in the phase lock loop is from the phase lock loop bandwidth. A wide bandwidth makes a loop more sensitive to amplitude fading, thus loss of lock. A narrow bandwidth makes the loop more robust but filters out phase scintillation effects. The loop can be configured to have a narrow loop bandwidth but still provide wide bandwidth phase data. Now, I should say that the WAAS system right now, the FAA is designing the new WAAS receiver to include a dynamic phase lock loop for their receiver. So it's going to have both a low bandwidth and a high bandwidth, and they have an error signal threshold, so they're going to jump back and forth between the two bandwidth loops, and that's really the way of the future. I think that it's going to help us track through a lot of the phase issues that we have now. So in the future, we're also going to have new GPS frequencies. They're going to enhance both scintillation and TEC monitoring. GPS is going to add a new signal at L2. It's open-coded, so it doesn't have the problems that we have now with selective availability on L2. And L5 is also going to be incorporated. I think there's a couple of L5s up there now. So L2C is going to be on 8 Block 2RM satellites, and L2C and L5 are going to be on all subsequent Block 2F satellites. Future SBAS GEOs will broadcast at L1 and L5, and the first Inmarsat 4 is already on orbit. FAA is going to be adding new payloads with significantly higher power, and Galileo is going to have open-coded signals at L1 and L5, but not at L2. So again, just to give you a sense of GPS modernization, the present signal, and I should say we already have some of the L2Cs up there. The initial signal was L2 and L1, but we now have several satellites up there. I think there's 7 with L2CS, which is a much better signal than the CA on L1. And we also are getting, with the second step, a new signal on L5. So we're going to have more frequencies and better signals to help us in this area. And we should not forget that GPS is no longer the only game in town. We have GLONASS, which I think has almost a full constellation now, and it's going over to code modulation, CDMA kind of signal like GPS, which is going to help us. GLONASS has the advantage that it's at much higher inclination, so we can track satellites in the polar region at higher elevations, which will help us. We also have COMPASS going up there, Galileo, and EGNOS. So there's going to be a lot more signals available to us, and some of the new receivers are already offering this capability. So the more signals you have, think about that one chart I showed you where when we had a time of scintillation, 1 satellite out of 8, but there was one, was not actually seeing scintillation. The more signals you have, the better off you're going to be. So with that, I'm going to turn it over to Joe Kunches.
Thanks, Anthea. You've just heard, I think, a really good summary of some of the technical solutions to trying to solve the problems that the ionosphere brings. looking at different receiver issues, different signal issues. The satellite constellation being filled in will be a big help, certainly. And what I want to talk about here at the end is some other things you can do in terms of following situational awareness and knowing what's going on, so you can kind of plan your day or the next few days in terms of what space weather might do to the plans that you have. The first thing you can do is you can go to the Space Weather Prediction Center website and focus in the middle of the page on the current and past 24 hours space weather conditions, and particularly make note of what's going on with the geomagnetic field. And just in round numbers, for mid-latitude users around the world, a G2 category 2 level magnetic storm, which would be classified as a moderate level disturbance, may be strong enough to cause some issues with both phase and amplitude. Of course, that isn't a perfect recommendation, but I think if you wanted to sort of dial in at a particular level, that would be the one that I would suggest. Now, if you know that there is a storm that is forecast, and for example, about 4 hours ago, there was actually a small coronal mass ejection, kind of a slow coronal mass ejection, I should say, that went by the ACE satellite and caused a short-lived little pulse to the Earth's magnetic field. And just for your information, there's going to be another one probably in another day or two, that given this time of the solar activity cycle, the sun is going about its business, doing what it wants, and sometimes we get in the way of these ejecta and sometimes we don't. But suppose you know of an impending storm. You can also go to the Space Weather Prediction Center website and actually watch the coronal mass ejection model as it goes about its business. And I'm just going to play a film loop for you here now. Oops. For some reason it didn't want to do that. Let me try that again. Okay, there it goes. Showing again a pulse that in the green line that it's about to pass is the prediction for when that CME was going to go by the Earth. So if you're made aware of the fact that there was a coronal mass ejection, you can go to the website and you can see what the model is predicting. Maybe I can run this for you again so you can watch it. And you can actually track, and you can be a forecaster too, and see if you think this is going to go by the Earth, and if it does, when's that going to happen, and and so you can be more of an active participant in the whole process. Now, if you know that there is a storm in progress, if back to the first slide I showed you a minute ago where you saw that there might be a G2 or a G3, or back to the Halloween episode in 2003 where we hit G5 storms, you can check to see the conditions in near real time, and in this case it's over North America, of the ionosphere by virtue of the total electron content. There's a cores, NOAA has a reference grids, number of stations that are put in permanent spots that do dual frequency measurements that send their data with others. The GPS Met and IGS also contributes to this, that give us a sense of what's going on overhead, and then we can map this for you to see. And what I'm not showing you much in the picture that's on this page, but if you see rainbows, if you see big gradients on here, that's a good sign that you might be getting some diffractive effects from scintillation as a consequence of the space weather. Now there are other places to get the same kind of information. The German Aerospace Center has got their own maps that they produce, as well as JPL, and then one of the attachments at the end of our time today, you can get more information about where you can go if you think the ionosphere is disturbed, and the way that you could know that is by looking at our webpage, or better still, you could let us make the predictions of storms, and then we can notify you when we think one is coming. But suffice it to say that there are a number of places you can go now to see what is the state of the ionosphere in terms of the total electron content, try to get a sense of both the refractive and diffractive issues that come with the bulk TEC that the signal is going to experience, as well as some of the structures that may cause it to scintillate. And you can get alerts, email alerts from us as conditions evolve. So just to make a quick pitch for this, it's a free service. I again would suggest that you sign up for a geomagnetic storm scale of G2 or greater. There is no fee to register, and if you drill down and you go through the registration process, this is where you would go to sign up for that. If you want, you can sign up for more alerts, warnings, and watches for radio blackouts, say, if you have some consideration about high frequency communications or even the rare solar radio bursts that might affect GPS on the day side of the Earth, as Anthea talked about. You can sign up for solar radiation storms if you're interested in that, and various other things. So we're here, we're here at your disposal. We're here 24/7, putting out alerts, warnings, and watches. In this way, we can send you notifications so you can start to formulate a plan if you see things start to go badly for you. So I'm going to stop here and turn it back over to demos and see if there are any other questions and how we want to proceed.
Thank you, Joe. All right, so as far as the material we're going to present, this is it, but we'll open up the floor for questions shortly. But before we do that, let's take one final poll. So, Lori?
Okay, we'd like to hear from all of you. Which of the following actions do you plan to take regarding space weather? In this case, you can select all that apply, so feel free to select more than one response. Update my GNSS user equipment in order to utilize modernized GNSS. Acquire hardware to monitor space weather effects in my local area. Upgrade existing monitoring equipment in order to utilize modernized signals, or take no action. Go ahead and weigh in on that. And as mentioned, we will be moving into the final Q&A period in just a moment. Why don't we go ahead and do that? I'll pass it back over to you, Demos.
Thank you. I mean, hopefully you've got a lot of information out of our presentations today, but if you need more info, there are a couple of resources that we've put up here for you. So you could go to the Novotel website, our sponsors, to see about products that would help with space weather. Then you could visit the Inside GNSS website as well for the PDF of this presentation, as well as there will be a list of resources that we'll provide. And last but by no means least, you may want to consider, if you want to learn more about space weather, attending a space weather workshop in Boulder later on this actual next year, coming up soon though, at the website that we have at the bottom of the slide here. And with that, I think we will stop here and I guess open the floor to questions to our experts. All right, and let's see, we've had lots of questions, so let's start with the first one. It's a question from Orlando, and I'm going to ask Jason from Novotel to answer this one. And the question is there any technology to mitigate the effect of scintillation for real-time GNSS applications, either RTK or precise point positioning in South America?
Well, I think Anthea covered quite a bit of that in the second part of the presentation, but definitely, we see multi-constellation and multi-frequency receivers performing much better in the field in most applications. Specifically, when you have more satellites to track, we saw in some of the plots that Anthea showed, this can be quite a localized effect in the sky, and the more satellites you have available, the more likely you are to have some signals to hold on to. So really that's the best bet that we have for mobile applications. For stationary applications or for scientific purposes, we could do some of the things that Anthea talked about with getting a better clock source into the receiver and playing around with the tracking loop bandwidths. But that's really aimed at kind of the scientific community and people that want to monitor the localized effects of the ionosphere.
All right. And Anthea, is there anything you'd like to add to that, or?
Well, no, I think he just covered it.
Okay, great. All right, so let's see. Next question, I guess this one we'll ask Joe to answer it, and it comes from Matt. And it's how strong, it's a question on how strong would a geomagnetic storm KP index need to be to affect GPS in the mid-latitudes, I guess lower 48 states in the U.S.?
Yeah, it's not a perfect answer, but in round numbers, I would look at G2 level, which if you like KP, that's more like a KP of 6. If I'm confusing you with another index, go back to the NOAA Space Weather Scales and just focus on moderate level geomagnetic storms. It's very hard. I think we all appreciate the problem. It's not only the environment and the sun and the ionosphere going about its business and becoming disturbed and quiet and stormy and otherwise. The technology has evolved and continues to evolve, where it's so dependent on the kind of activity you're trying to do and the conditions whatever you have, the horsepower you have in your receivers and your antennas, and how much time you can spend on station, that it's hard to give a one good answer to everybody. But again, I'd start looking at G2 level.
Thank you, Joe.
I can say something there.
Please do, Anthea.
I think that you actually do see SED effects at KP equals 3, but whether or not they would affect your GPS receiver or GNSS receiver, that I don't think so at KP equals 3, but we clearly see the storm enhanced density feature at values that low.
Thank you. Well, here's another one for you, Anthea, and it's from John. And the question is, has anyone observed large ionostorm gradients in the equatorial regions similar to what has been observed in CONUS?
The answer is yes. I'm a little confused about that question, but I think there's a famous Minucci paper et al. Which shows over the ocean, actually, huge increases in the TEC. And that's actually more, it's not exactly in the equator. The equator basically is going to have depletions during the storms, but it's going to have large gradients as well.
All right. Let's see. So here's another question, and this one is for, I guess I'll send it to Joe. And the question is from Ken, and says the National Geodetic Survey user guidelines for single base real-time GNSS fishing recommend no GNSS and G3 to G5 geomagnetic storms, or S4, S5 solar radiation storms, or R3 to R5 radio blackouts. Yet space weather predictions don't always give predictions in the above scales. How can I correlate prediction parameters with NGS GNSS recommendations?
Yeah, Ken, you're right, and we've taken note of that, and in the next 60 days, what you're going to see is, if you are a subscriber to some of our daily routine forecast products and such, you're going to see all of that in terms of the NOAA Space Weather Scale, these G, S, and R indicators that you're talking about there. The other good piece to this is that if you choose to subscribe to the email alerts, warnings, and watches, those are all in terms of the NOAA Space Weather Scales, so it's all converted for you there right up front. But we have received that feedback that some of this is very confusing to people, and we're trying to fix that.
Thank you, Joe. I guess this one is for Anthea, and it's from Rajesh, and I guess it's a question on clarification on phase scintillation. When you talk about sigma phi, are you talking about 1 second or averages over 60 seconds?
Well, that's a good question, and everything you saw in my talk here was 60-second average, which is what I personally prefer to use, but it is typically defined at 1 second, 10 seconds, 30 seconds, 60 seconds. So what I showed you was 60 seconds. That's what I personally prefer. I'm not sure which is the best one to use. I think it depends a little bit on what physics you're actually looking for.
Right, thank you, Anthea. Let's see here, the next one, I guess I'll direct this one at you, Joe. And the question is, could you talk a little bit about the efforts at SWPC and elsewhere to use models that ingest real-time data instead of climatology, such as GAME, to produce warning products of sufficient accuracy to be useful to GNSS users?
Yeah, this is a good story, because probably in the last 15 years, maybe a little bit longer than that, with the with the explosion of GPS, GNSS-based applications and different very imaginative, creative things, we've become painfully aware that we need to both monitor the ionosphere, but better than that, predict the conditions that are going to affect these applications. GAME is the Global Assimilation of Ionospheric Measurements. It's been a model that's been around for a few years. A couple renditions of it is one example of trying to create, and the scientists are working hard on this now, a physics-based predictive model similar to, maybe it's not similar, but think like the weather models that are so commonplace anymore, that can look out a few days, sort of going from, say right now there was a coronal mass ejection that was launched from the sun. If we thought it was going to impact the Earth in 2.5 days, then the physics-based ionospheric models would then kick in to say, okay, given that, what's the ionosphere going to look like in 4 days out? And both in the military and on the private side of the fence, we know we're working hard to try to be smart about how we can best serve our customers, and smack dab in the middle of that is the physics-based modeling effort.
All right, thank you, Joe. Let's see, here's another question, which I will, let's see, direct at Anthea. And it's from Pavel, and it's, how would you describe the connection between the magnetosphere indices, KP, and the state of the ionosphere, TEC? Would there be correlation in these data?
Well, there would be correlation. TEC, as you know, depends on it depends on time of day, it depends on solar activity. It means if we're in the solar minimum, we're going to have less TEC than we are during solar maximum. I would say that at least over the continental U.S., when we see a KP equals 3, and it's about, we see this at 1500, between 1500 hours and say 2400 hours UT, you will see some kind of disturbance. So that's kind of really narrowing the field here. But I do think that when you have KP equals 9 effects, very, very large disturbances, somewhere on the globe you're going to see a problem. But it depends on what time of day, where you are, what's happening, and what's going on with the solar cycle to know how much effect there will be. Joe, would you say any more there?
Yeah, and I think, Anthea, the other part of it is that KP is an index, and it's a global index, and, you know, love it or hate it, it's got a long history in space physics and the ionospheric physics community. It's a little bit like the Dow Jones or the Standard & Poor's indices for the stock market. KP actually is a 3-hour index. It's, to make it, you need a number of magnetic observatories, you know, distributed at different points around the world. We do a real-time KP, meaning that at the end of every 3-hour mark we'll tell you what it is. That's based on about 8 magnetic observatories. That network spans from France to the UK, through Canada and the US to Korea, and we get that information, and we try to give some general indication of how disturbed the Earth's magnetic field is. But as you point out, you know, TEC is a line of sight local measurement that has some relationship to that global index, but not a perfect one by any means.
All right, thank you, Joe. Let's see, here's a question, and it's for you, Anthea. And it's, are polar scintillations, which affect GNSS, constant or only present when CME events occur? I guess this could be for both Joe or Anthea.
Well, I'm going to try this and see if Joe can agree with me. One, polar scintillations are pretty much, they are somewhat seasonal, and they are related to CME events, but they're not only present during CME events, so you shouldn't, you'll probably see them more, but certainly CME is not the one thing you should look at. And there have been some recent studies, kind of morphological studies done by the Italian group, which kind of give you a sense of when and where you'll see them as a function of position MLT, which is magnetic local time. So I would refer you back to some of those studies, and the person who wrote that was Lucilla Afonsi, and it was in Radio Science. And Joe, do you want to say anything more about that?
Well, there's a lot of interest in trying to understand the ionosphere at the polar regions now from geophysical surveyors, from just the things that are now different up there than they were 10 or 15 years ago in terms of transportation and search and rescue and on and on. And I think we're hearing from users that they want good ionospheric forecasts for the poles and actually a little lower latitude down in the auroral zone. My sense is that the solar wind is pretty much a direct driver for scintillations in the polar regions. So if you were to watch the ACE satellite data come in, you'd be very situationally aware of what the conditions were in the polar cap. If you go a little lower latitude than that, down in the auroral zone, it's more like the traditional geomagnetic indices in terms of phase scintillation that relate to the electrojet current systems in the auroral zone. So, but I guess my sense is that that's a really hard place to study the ionosphere. Things move very quickly at high latitudes, and it's very challenging for the scientific community.
All right, so I guess maybe we have time for one or two more questions, but let's go to this one. And Joe, I'll give this one to you. It's from Luis. And it is, the question is, does the NOAA space weather prediction usually refer to time tags when the energy left the sun or when it will arrive at the Earth?
Yeah, we'll give you both. In our text products, we'll say what time the coronal mass ejection left the sun, as well as when it is expected to arrive at the Earth. For the alerts, warnings, and watches, you'll get the arrival time at Earth in those products.
All right. Well, I guess this is a question. I'll answer it. There's been one or two questions about the list of websites at the end that we talked about in this presentation. The material that we'll post up on the website will have that information. Let's see. Here's another question, and I guess I could give it to. I'll let both Anthea and Joe answer. But first, let's see what Joe has to say about it. The question is, what is the reliability of space weather predictions? What are the frequencies of both misdetections and false alarms and so on and so forth?
Gee, I think we might be running a little short on time. It's a long way. The 93 million miles from the sun to the Earth allows for, a lot of room for things to change en route. But seriously, we're well aware of the fact that we need to beat down the false alarm rate with the imagery and the information now that's available to us. If you just go back and you look at the sun, sometimes, daily or more than that, you're going to see all sorts of stuff going on in the X-rays, in the extreme ultraviolet, in the hydrogen alpha lines, and so on. And really, the trick for forecasters is to know what not to pay any attention to, and so as a consequence, we try, by virtue of this physics-based model I showed you, the pinwheel model, to quantify as best we can what's coming. I can tell you that let's talk about coronal mass ejections coming from the sun, that in terms of arrival times, the times that we predict, like again, let's pretend a CME is launched right now, and our model would say in 37 hours it's going to go past the Earth. We're within about plus or minus 5 hours over quite a few years, couple of years of using that model. So we feel pretty good about that. The harder thing is getting the magnitude of the storm, because that's a physics problem. That's a nut we just haven't cracked yet.
Anything you'd want to add to that, Anthea, or?
Well, I should say we're trying here to predict some things, and we have we don't just depend on NOAA, actually, and so far we're not doing a good job here. So I think this is still something that nowcasting is probably the first thing to do, and then forecasting is something we need to work on. Would you agree, Joe?
Yeah, I would say situational awareness. You know, if you can know what the conditions are now, and then in terms of the short, you know, maybe day out forecast as far as looking for a change to the space environment near the Earth, that means a geomagnetic storm for GPS users mostly. You know, again, I think we're better than we ever were in seeing these things come off the sun, and but I think it's the right answer to say that situational awareness. Look at those TEC maps and focus on those, because if you see a structure in those maps, chances are it's going to be around at least for a few more hours.
All right, thank you, Joe and Thea. And unfortunately, there are more questions, but we just don't have enough time to go through them all. So I guess we'll need to wrap it up at this point. So I guess I will move over to I guess let our sponsor have I guess some closing remarks here.
Well, thanks everybody
Jason.
for joining us today. It's been Novatel's pleasure to sponsor this webinar on such an important subject for users of GNSS. A special thank you to our moderator Demos and our speakers, Anthea and Joe. If anyone is interested in getting more information about Novatel's space weather monitoring products or our family of multi-frequency, multi-constellation receivers and antennas, feel free to contact us at novatel.com.
All right, thank you so much, Jason. And folks, before we sign off, we would like to thank each of you for joining us and trust that you found today to be of value. Special thanks to Joseph Kunches and Anthea Koster, and of course to our sponsor and co-host, Novatel and Inside GNSS. Note that you will be receiving a short survey at close today, and we'd certainly appreciate your filling it out. Also like to extend a quick thanks to our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. A copy of today's webcast will be available for download, and you'll all be receiving a link from us in an email early next week. And most importantly, thanks for joining us. This is Lori Dearman saying have a great rest of the week. Bye for now.